Good evening, everybody. Today, I welcome you all for the session of LTI system representations, linear time invariant systems representations, which is coming under VTU for 4th semester students studying in module 2. And it can also be studied. Any other branch students also. Whoever interested, any student who is interested in LTI systems representations, right, in time domain, they may study, right. Whoever wants to do MTech thesis, PhD in signal processing also, they can use this LTI systems representations of signals, right. Now, these are continuation sessions of my previous LTI systems representations. In the previous sessions, we discussed about LTI systems, how to represent LTI systems x of an input and output in time domain, right? And where in the previous sessions we discussed, right, x of an input, right, x of an input and y of an input to represent in terms of shifted impulses. And we have shown last class how to represent this x of an input in terms of shifted impulse, and we have shown this also. We have represented x of an input in terms of shifted impulse by using these equations. K is equal to summations minus infinity to plus infinity x of k delta of n minus k. That means each input of x of n, for example, if I take any input x of n, we can represent each sequence right, in terms of shifted impulses, and we have shown that problem also. Now today we will see if input is represented in terms of impulses, output of LTI systems can also be represented in terms of shifted impulses only. Let us do that, right, in LTI systems. Right, for that, if I prove that the y of n, represent that y of n in terms of shifted impulses, then there is also nothing but convolution sum. This is very, very important in signal processing. Convolutions, this technique is also nothing but convolution sum. What do you mean by that? If you consider LTI systems and if you do it, right, for discrete time sequences x of n, h of n and y of n, then the concept, the term which you are using to calculate LTI system is called convolution sum. If you do the same LTI systems, if you represent for continuous time signals x of t, h of t, then y of t, then this same, right, the output is called convolution integral, where instead of sum we are writing integral. That is what your next half of the module. First half of the module is convolution sum. That means discrete time sequences we will consider, we will write the answer. Right, now let us see convolution sum. Listen carefully, convolution integral is just wherever x of n is there, x of t, h of n is there, h of t, y of n means y of t, that's all. Now, first consider for this convolution sum derivations, one little derivations, where to calculate output, consider LTI systems where x of n is input to the systems, y of n is output of the systems, h of n is the system impulse, and t transfer of is a system operator. That's what it is. Now see this, h of n is system impulse response. This is full system impulse response is nothing but h of n, and transfer of is nothing but is a system operations which you are doing it to the input. Now for example, to derive the output, first we can write y of n as your output. This y of n output can be written as y of n is nothing but transfer of x of n is nothing but y of n. Y of n is nothing but transform of x of n gives you y of n. That's what first line. Y of n is nothing but transform of x of n input. Now, you know how to write the x of n input in terms of weighted sum of shifted impulse in previous class. X of n is defined by shifted impulses. I shown you last sessions how to write it in terms of shifted impulse by using these equations. K is equal to minus infinity to plus infinity, x of k delta of n minus k. Just substitute here using weighted sum of shifted impulses, y of n becomes transform of what is x of n? X of n is this summation k is equal to minus infinity to plus infinity, x of k, delta of n minus k. Now, here, this is x of k is there, delta of n minus k is there. Now, using linear property, we can take out this x of k summations first, and we can write transform of delta of n minus k. That's how I will write. First, using LP, linear property, you can write summations k is equal to minus infinity plus infinity x of k one term into transform of delta of n minus k, which I want. Call it as equation number 2. Then, transform of delta of n minus k is nothing but this corresponds to operations of the system performed on time shifted impulse delta of n minus k. That's what transform of this is nothing but the operations which are doing it to this time shifted impulse delta of n minus k. Now, using time invariance property, we can write the transform of delta of n minus k shifted pulse as h of n minus k. What is h of n? Where h of n is nothing but total impulse response of the systems, full system. This system's impulse response is h of n total. A delta of n is nothing but shifted impulse, right? That is for one pulse. This is for the system. Now, therefore, we can write transform of delta of n minus k as h of n minus k. What is that? System impulse response, h of n minus k in terms. Now, substitute these two here, you will get the equations. Where h of n is nothing but impulse response of the systems. That is, therefore, equations can be written as y of n is equal to summation k is equal to minus infinity plus infinity x of k into h of n minus k. What is transform of delta of n minus k? Which is nothing but system impulse, right? H of n minus k. Therefore, this is what is standard equations. Y of n is equal to convolution sum equations. Output y of n, therefore, can be written as x of n linear convolution with h of n, which is nothing but summation k is equal to minus infinity to plus infinity x of k into h of n minus k. This is nothing but convolutions equations, equation 3. What this says that using these equations, if input is in terms of shifted impulse, then from this equation we can express output of LTI systems also is written in terms of weighted sum of shifted impulses only. That is what this. Weighted y of n is equal to, if for example k is equal to 1, x0 into h of 1 minus k. If k is 2, x2 h of n 2 minus k. That means if input is expressed in terms of shifted impulse, then output is also, for example, if input is expressed in terms of shifted impulse, then output is also, output of LTI system is also expressed in terms of shifted impulse. That's what this. Now this we will understand. If I take one example, one problem, then we will know how to write y of n also in terms of shifted impulse using this simple problem. Right? What is that problem? Find output of y of n of LTI systems, on LTI systems, having input x of n given by this x of n, and impulse h of n is given by this. Find y of n. What is giving in LTI systems? He is giving x of n, and he is asking, and he is giving h of n. Right? He is asking y of n. Okay. Right? Now x of n is giving us 4 samples. That is, x of n is equal to 1, 1, 0.5, 0.5. That is 1, 1, 0.5, 0.5. At 0 it is 1, at 1 it is 1, at 2 it is 0.5, at 3 it is 0.5. Now see, this is nothing but, if arrow is there, at n is equal to 0, x0 is 1. Then right side. Left side is minus 1. Now, similarly he is giving h of n. Again 3 samples. At 0, 1, at 1.5, at 2.5. That means h of n is equal to 1, 0.5, 0.5. 2 samples, 3 samples is given. This is 3, this is 4. 4 length sequence, 3 length sequence. Now to find y of n using the same graphical method. First, just it's very very interesting. If you learn one, the rest is n methods are there. This is the easiest method, graphical method. The output y of n is obtained by adding responses to each individual samples of input. For example, each individual sample shifted impulse form you have to write. For example, how many samples are there at input? 1, 2, 3, 4. 4 separate samples, individual samples you have to write. At 0 it is 1, at 1 it is 1, at 2 it is 1.5, 3 it is 0.5. That means 4 individual samples. Now see, 4 individual samples. At 0 it is 1 individual sample. At 1 it is 1, that is second individual sample, x2. Then at 3, sorry, then at 3, for example, x1 and x2n, and then at 3, for example, at 2.5, at 3.5, x3n, x4n. Then finally add all individuals. And you will get some responses now. That responses you have to add. Now, first let me write first one, x of n is this, h of n is this. First write x1n, right, x1n, first sample let me write. x1n is equal to, I know this last class also, x0 at delta n, its value is 1. Now see, what is x0? See, at x0 its value is 1. That is x0. Delta of n at this point, the impulse is delta of n. At this point x1 at 1 is 1. Delta of n minus 1. At this point delta n minus 2 into x2. There x of 3 into delta of n minus 2. That is how I am writing. First sample I write. x1n input is equal to x0 into delta of n. x0 is 1. Delta of n is 1. 1 into 1 is 1. That is why first sample I am writing individual. Right. Similarly second sample, individual sample is equal to, let me write first input. Second sample is x at 1 and delta of n minus 1 at this point. Now I am writing that one. Now see, x2 of n is equal to x at 1 into delta of n minus 1. See that x at 1 is 1. Delta of n minus 1 is 1. 1 into 1 is 1. That's what this. Similarly x3. x3 means, see this, x2 into delta of n minus 2. That is 5. Find 5. Now see, that is what I am writing. x3 is equal to, x3 is equal to x at 2 into delta of n minus 2. x at 2 is 0.5 into 1 delta of n minus 2. That is equal to 0.5. That is how we get this individual sample. x3n. Similarly, last one, x4n is equal to x3. See this? x at 3 e into delta of n minus 3. That is 0.5. Now, that is what I am writing. X at 4 is equal to plus all these here. x3 into delta of n minus 3. That is x at 3 is 0.5 into delta of n minus 3 is 1 is equal to 0.5. That's how you are getting this individual sample. First work is write x of n all individual samples. If 4 samples are there, 4 individual. And finally add left hand side. Now go to the right hand side. First, for the first case, x1n after writing first individual samples of input, then write h of n. See h of n. What is h of n? H of n is this. 3 samples are there. H of n at 0, 1, at 1.5, at 2.5. Now take this h of n first time, multiply this with individual samples. First individual samples. For example, see, take this h of n, multiply this with individual sample. You will get y1n. For example, multiply each samples of h of n, and take each samples of h of n, multiply with this, that individual sample. For example, here it is, at 0 it is 1. Therefore, 1 into this sample, 1 into at 0. 1 into this 1 is nothing but 1. See this first. y1n at 0, 1 into 1 is 1. Then, second, at 1 it is 0.5 is there. 0.5 into that 1. Every time take all these things and multiply with this individual. Take all these things, multiply with the second individual, like that. Now see, therefore at 0 it is 0.5. 0.5 into 1 is 0.5. Then at 2 its value is 0.5. 0.5 into 1. Now that's what, now next see, that 0.5 into this 1 is nothing but, 0.25 into 1 is 0.25. Therefore this is what y1n. Similarly, go for x2n, for example. Second time, write x2n individuals, then right shift this h of n by 1 second. See this h of n, right shift this by 1. What will happen then? When you right shift this, you will get your h of n now as 1 minus n like. 1 minus n like, for example. At 0, for example, 0 here maybe. For example, at 0 now, you will not have anything. At 1 you will be having whatever you are having. This sample, one shift. At 2 you will be having whatever you are having at, this is 1, this is 0.5. Then at 3, one shift, that's all. At 3 it is 0.5. Like this you will get. One shift you will get, that you have to multiply with second pulse. For example, take that right shift by 1 and multiply with this, all that with individual samples at 1 is equal to 1. What will happen? For example, then y2n starts from 1 because you are shifting 1. Your h of n, you are shifting it to right side by 1. Therefore, your sequence starts from 1 now. At 1 it is 1. Now see, at 1 it is 1 now. At 1 is 1. At 1 is 1. 1 into, for example, this 1 into second individual sample. At 1 into second individual sample is this, right? 1 into 1, 1. Second, 0.5 is there. 0.5 into 1, 0.5. At 3, 0.25 into 1, 0.25. That means shifted sequence you will get. Similarly, first you write h of n, then right shift by 1, again right shift by 1 more. Further right shift by 1 more seconds. What will happen? Then your y3 starts from, instead of 1, it starts from 2. Your h of n becomes like this now. H of n shifted by 2. For example, at 2 it is 1, at 3 it is 0.5, at 4 it is 0.5. Then like that actually, right? What will happen? It is, it seems this is 0.25. Sorry, you can change this. This is 0.25. It is not 0.5. Right? There it is, both are 0.5. Now that's why it is here also this is 0.25. Therefore, the answer is here 0.25 every time. Correct. Now, right shift by 1. What will happen? When you right shift by 1, your sequence starts from 2. Therefore, see, at y2n is at 2. 0.5 into, here 0.5 is there. 1 into 0.5, 0.5. Then 0.5 into 0.5 is 0.25. Then 0.25 into 0.5 is 0.125. That means, take this shifted pulse by 2, multiply with the individual samples of 0.5. Then lastly, similarly last one, y4n. y4n what you should do? Right shift again by 1. That's all. Once you may find tough. Afterwards it is easy. Right shift again by one more. Then your sequence starts from, instead of 2 it is 3. Right one shift. For example, write one more shift here. Your sequence starts from 3. 3 you will get 1. 4 you will get 0.5. 5 you will get 0.25. Then multiply that with the individual samples of LHS. LHS remains same. Now see, therefore what will happen? Right here, then multiply that way. Last sample is, it is actually 0.5. Right, x of n, no? 0.5. Then what will happen? Your y4n is, at 3 it starts from 0.5 into 1 is 0.5. Then 0.5 into 0.5 is 0.25. Then 0.5 into 0.25 is 0.125. Like this y4n you will get. In the end, add all x of n. X of n is nothing but individual samples of x of 1n, x2n, x3n, x4n. You will get your input. No problem. H of n is your this h of n. Your h of n is this h of n. Your y of n is nothing but add all y1n, y2n, y3n. This y of n is nothing but, for example, this y of n is nothing but here. Y of n is nothing but y1n plus y2n, all this, plus y3n plus y4n. You should add all these samples, right side. Now for example, at 0, see there, see now, at 0, y0n is nothing but 1 is there. At 0, nothing is there. 1 plus 0, again, plus 0, plus 0. Therefore, at y0, it is 1. Now similarly, at y1, add all 4. At y1, what is there? Just see. At y1, it is 0.5 is there, 1 is there, 1 plus 0.5, 1.5. Then, here nothing is there at 1, nothing is there at 1. Therefore, at y1 is 1.5. That means, add all 4 samples, amplitude and write it here. Similarly, y2n, you will get 1.25. y3, add all 4, you will get 1. y4, 0.325. y5, 0.125. You will get output like this. Y of n, the answer. At 0 it is 1. At 1 it is 1.5. At 2 it is 1.25. At 3 it is 1. At 4 it is 0.225. At 5 it is 0.125. Therefore, we can write this y of n as in the end. See that? Y of n as 1 into delta n. See this? At 0, what is the impulse? In terms of impulse, I am writing. At 0, what is the impulse? It is delta n. At 1, what is the impulse? Delta n minus 1 into 1.5. That's what it is. At 0, it is delta n into 1. At 1 it is delta n minus 1 into 1.5. That's what this. 1.5 into delta of n minus 1. Then similarly, at 2, impulse is delta n minus 2. Delayed by delta n is delayed by 2 into 1.25. That's what I am getting. 1.25. Now see 1.25 delta n minus 2. Similarly, third one is 1 into delta n minus 3. See that? 1 into delta n minus 3. Fourth one is 0.325 into delta n minus 4. 0.325 into delta n minus 5. N minus 4. Lastly, it is delta n minus 5 into 0.125. That is 1. 0.125 into delta n minus 5. What's the meaning? You will get here the output also is represented in terms of shifted impulses. Right? By using convolution sum, right? If input is expressed in terms of shifted impulses, x of n input to the system, then output also we are getting from convolution sum is also in the form of shifted impulses. This is how output is expressed in terms of shifted impulses using convolution sum in LTI systems representations. Now what's the benefit? What's the benefit of this? Right? Here the signals we can study. Right? Both LTI systems is represented input and output in terms of time domain only, in terms of shifted impulses. Shifted impulses means what is the advantage actually? Now see, in your example, each individual samples is being studied in terms of shifted impulses. That means if input is having 4 samples, each one we are studying with respect to impulses. That means you will not miss any information when you transmit and receive. You can analyze everything. You will not get anything right. If you get any error, you will know, you will understand, because efficiently you can study, and this gives flexibility to the signals processing actually. That's it. Now see, at 0 it is written in terms of shifted impulse, at 1 in terms of shifted impulse. Similarly, output is also in terms of shifted impulse. This gives more flexibility. That convolution sum gives more flexibility to the signal processing, and without error we can transmit signals and we can receive signals. I hope I am very clear, right, in these sessions about right, input and output written in terms of impulses. Next sessions maybe will take up the problems on, this is graphical method. This is graphical method of, we have shown convolutions. Next method will see the convolution sum, how to get y of n in terms of formula or in terms of tabular column. We'll check all that, right? That gives flexibility again, right? Till that, right? It seems, right? Thank you very much. Have a wonderful day.